Okay. Gustavo?
So hello, sorry. Hello and welcome everyone to our Digital Futures Young Biodesign panel that kicks off our 2021 season of events, workshops, and worldwide conference scheduled for this summer of 2021. If you have not done so, please sign up for our newsletter that will be linked on our website and stay connected with our Digital Futures community and family. Our Digital Futures Young team and I wanted to give a special thanks to Philip Yuan and Neil Leach for all of their dedication and inspiration over the years. Today's presentations will be co-moderated by Victoria Huisi Barbo and I, Gustavo Rincon. Let me say a few words about myself. I'm educated as an architect, and I'm a recent PhD graduate from the University of California, Santa Barbara. I'm affiliated with the Allosphere Research Group, located at the California Nanosystems Institute at UCSB. The topic of my dissertation was titled Shaping Spaces as Information, a Conceptual Framework for New Media Architectures. A core area of my research and my grounding for the creation of a new field of inquiry was the integration of architectural methods demonstrated in prototypes for the arts and sciences, with the study of complex system science and the application of algorithms, agent-based models at the biological level to the atomic scale works exploring the quantum with Dr. Kuchera Marin. I am inspired every day by the wonder of nature and our universe. The biggest challenge for our profession is to evolve and to stay vital for future generations. As the newest member of the Digital Futures Young Group, I am honored to be a part of a community of practitioners and researchers that strive for the accessibility of knowledge to positively influence change within the architectural field. I am honored to introduce my colleague today, Victoria Luisa Barbo. She is the principal of Resonant Matter, a multidisciplinary practice focused on the intersection between natural, built, and digital environments. Victoria is a designer and independent researcher interested in ideas surrounding the cultural and spatial effects of perception and ecology. She previously organized the Ecological Thinking panel discussion and the Biodesign panel for Digital Futures World. She is my esteemed colleague, and without any hesitation, she represents our profession's finest ideals. Let me explain the structure before moving forward. Victoria will be introducing the Biodesign's panel's motivations and problem statements. That is an area of research of Biodesign solves. Victoria will briefly introduce the field of biodesign, the panel's motivations and core questions. We will then go to each of our individual panelists for presentations, and then we will proceed to our first discussion with some questions that will frame our understanding of the field of biodesign. What is it? How did we arrive here at this moment in time? And why is biodesign research essential for our future as a human species? I will now pass it over to Victoria.
Hi, everyone, and Happy New Year 2021. Today's panel will highlight a new generation of architectural researchers that are part of the biodesign field. And we will build on the discussion that has been established in our two previous events on ecological thinking and biodesign. So please check them out if you're interested here on YouTube. But for those who are not very familiar with the subject and are new to the topic, to give a little clarity on what the field encompasses, I want to make give a few words, a brief introduction on the field of biodesign. What is biodesign? Bio is Greek for life. Thus, as the name implies, biodesign is a part of a larger movement that focuses on the incorporation of more organic life and with it, organic systems of intelligence into the human lived reality. Designing with biology is nothing new. selected breeding of plants, for example, to make them more sustainable and suitable for human needs is one of civilization's oldest practices. But the emergent field of biodesign goes much further. It crosses traditional boundaries between fields. Biodesign combines the interest of the life sciences like biology, botany, bioengineering, and much more with design and architecture to explore new solutions and technologies and to incorporate those in the real world, to address hidden issues in our lives like environmental destruction, overproduction, consumption, and so on. There are many approaches to the biodesign field, and we will see a variety presented by our guests today. But as a means of introduction, I will also show a few other examples here. So there's different approaches, as I said. One of the approaches is the material-based approach. It's focused on incorporating the use of living materials or moist media, such as fungi, algae, yeast, bacteria, and cultured tissue. Projects do not only take inspiration from, but incorporate natural systems. These designers harness natural systems to benefit from their performance, storing and converting energy, producing oxygen, neutralizing poisons, and so on. This field is famously represented by Neri Oxman and the mediated matter group at MIT, but there's many more designers that have that kind of path. For example, here, another project by David Benjamin and the Living, built by mushroom bricks, or here, a 3D printed mycelium chair. Another approach is biomimicry, and that has been around for a little longer. It's basically informing design through the imitation of biological systems, learning from nature's intelligence, its forms and informational systems. Here represented by Aki Mendez, but as I said, there's more to it, as always. And then we have another approach, which is the closed loop system approach, or ecological system approach. These projects emphasize sustainable systems based on natural resources in a way that means what is taken away can be given back. This means the creation of closed loop systems with a zero waste policy by integrating natural processes that are being allowed to flourish within a design system in order to create more sustainable methods of living, like, for example, a classic aquaponic system, as we can see here in the project by Matthew Lesnar. Or here, a project by Ecological Studio, one of our guests from a previous session, Claudia Pasquero. And if you're interested in seeing more about the fantastic work, go to our last session here on YouTube. And another project, which is also part of the discussion I just mentioned, Mitchell Joachim, his anti-extinction library. There's a lot to this project, so I recommend checking those out. And some of these closed loop practices are very old, and indigenous communities have practiced them for centuries, like we can see here, for example, in plant shaping structures, tree bridges in India. And that leads to another branch of biodesign, or designing with nature, that is more activist. And this more activist approach is questioning the relationships between humans, nature, technology, through multidisciplinary projects and collaborative efforts to learn from indigenous knowledge. As we can see here in this fantastic book by Julia Watson, Low Tech, Radical Indigenism. So biotechnology and biodesign have brought about a lot of changes and greener modes of production. We have benefited greatly from it, but it's also created new risks. So as biological systems find their way into the world of design and architecture, we as designers need to understand the concerns and benefits to design creatively, but also thoughtfully and ethically. Biodesign harnesses life. It introduces new capacities and raises new concerns. So I want to pose a few questions that I want to get back to during the discussion, but maybe it can already help the audience to kind of engage in it better. So what are potentials and risks that biodesign introduces to human and non-human lived reality? How does biodesign change the field of architecture and design? And how does biodesign address the systemic changes needed to address obstacles for global scale implementation? With that, I would like to give it over to our first presenter. So if you could share your screen, Natalie.
Yep, just sharing my screen.
Okay, I'll stop sharing.
Everyone can see this?
Yes, perfectly.
Okay, great. So hi everyone, my name is Alima. I'm from Australia, from RMIT University in Melbourne. Today I'll be discussing my research of the symbiosis of computational, robotic, and biological agencies. Let's minimize this. So basically what my interests are is this fusion between each medium of computational agencies, robotic agencies, and biological agencies. And through my research, I really explore feedback systems in which natural processes can work in collaboration with digital fabrication technologies. So what I'm quite interested in is how this multidisciplinary approach to architecture can really affect the way we produce form and the way that we as architects can design when designing with living materials. So a quick synopsis about my background. So I actually studied my master's at IPE University in Barcelona, and under the supervision of Marcos Cruz, I became really interested in this notion of parametric design and this hybrid between large industrial machines and small scale robotic biological materials, and obviously this multidisciplinary approach to architecture. Upon returning back to Australia, I worked at a architectural firm. But what was really missing when you enter the architectural discipline is, how to incorporate this research of biological materials and robotic fabrication within the real world of architectural design. So with this missing passion for working with biological materials, I returned back to academia. And I began my PhD under the supervision of Roland Snooks at RMIT University. And I began to run Biolab Studio, which is a studio run at RMIT University and Monash University as well. So the key questions that I asked within my research are what the design implications are when enabling biological growth to contribute to the creation of form. So rather than focusing on the streams of biomimicry, what I'm quite interested in focusing on is how does the growth of biological materials contribute to the creation of form? So how do we really enable nature to become a co-creator within the form-making process rather than mimicking its forms, such as designers do in biomimicry? And what the design tectonics emerge from these processes when material dictates shape. So how do we really create material-driven design processes? And then what are the research aims? So to embrace the unpredictable, the strange, and the highly volatile and unrestrained nature within the design process. So how do we really embrace nature's unpredictability and strangeness within our perfect world of design and architecture? So in order to embrace biological growth within the design process, I'm quite interested in robotic feedback systems. So how to create a feedback system between the robots, biological materials, and computational design. And then how to create these looped feedback systems between each medium so that they can create a direct dialogue between each medium. So the material that I work with is Mycelium. For those of you who are unaware, Mycelium is a fibrous root of a mushroom. It has the chemical characteristics to remove toxins from water, act as a natural binder, and biodegrade through a series of nutritious substrates. I'll just run through two projects quite briefly in this presentation. The first project is entitled Scaffolds. So this project really focuses on injecting liquefied mycelium into a series of biodegradable sacrificial 3D printed frameworks. So this project really took inspiration from innovative technologies currently occurring within the medical field. So technologies that incorporate biological materials with industrial machines. So fabricating, 3D printing artificial organs, or fabricating or bioprinting or biotransplants. The technology that I'm quite interested in is creating bioscaffolds. So this ability to design and fabricate these predetermined forms and then infuse a biological medium such as cells that would adapt and take over the entire host of the scaffold. So how this process works is the scaffold is 3D printed with a biodegradable filament. Simultaneously, this scaffold is inserted with the human cells. And then this scaffold is then inserted back into the human in order to biodegrade within its host system. So what my interest is in doing is how to create and how to mimic this technology occurring within the micro scale and then apply to the macro scale, so large architectural buildings rather than human bodies. So how have I applied that to Mycelium? I began to 3D print a series of biodegradable sacrificial formworks with this wood-based PLA filament. I then began injecting a liquefied culture of mycelium. So it's basically mycelium, but in a liquefied form with an injection. And then over time, the mycelium actually grows, degrades, and adopts the entire geometry of the bioscaffold, similar to the medical bioscaffold that's occurring within a human body. So what I became quite interested in is how to actually choreograph this growth and decay of the mycelium through form. So how to create forms that mycelium biodegrades at quite a rapid pace as opposed to quite a slow pace. So beginning to think about how to orchestrate this process of growth through form as the architect. So rather than allowing nature to grow randomly and naturally as it would within the natural world, how can I as an architect almost act as the orchestrator of this living growth? Through a series of tests, I began to discover that mycelium is attracted to quite fibrous and porous structures. As you can see here, I began to digitally fabricate these quite porous and fibrous forms that mycelium that would be inserted to and then eventually biodegrade. Here is just a series of a number of forms I've also been creating. So, you know, again, trying to orchestrate this sense of growth. So the smooth surfaces would prevent mycelium growth, and the quite porous fibrous surfaces would encourage growth of mycelium. So this is idea of creating one unified form that would encourage and hinder growth of mycelium. But then in order to incorporate robotic feedback within this process, I began to think, okay, so there's a distinct visual process between the living mycelium and dead mycelium. So living mycelium is quite fibrous and white in its exterior. Dead mycelium is quite brown and dried up. And then I began to think, okay, how can the robot react to both the living mycelium and dead mycelium and perform a series of different tasks when it notices when the mycelium is dead as opposed to when it's alive? So through color detection and robotic scanning, I began to develop a process which the robot would react to the living mycelium, which are the white areas, and then the dead mycelium, which is the brown areas. This was also tested through a series of other materials. This was actually done with student work within the RMIT design elective. So with slime molds, the robot actually reacts to slime mold growth by depositing other nutrients and orchestrates its growth throughout this large petri dish. As you can see, the camera here is detecting where the slime mold is growing, so detecting the yellow areas and then depositing more food accordingly. So it's this idea of the robot reacting to biological growth and how to orchestrate its growth through robotic intervention. So with this knowledge, I began to construct a unified tool. So once the robot would detect where the mycelium is growing, it would inject additional mycelium culture. And here is a soil sensor, an Arduino sensor, and here it could detect its moisture values as well. So with this knowledge and all these customized tools, the robot was now enabled to detect where the mycelium was living and where the mycelium was dying within the scaffold, and then deposited liquefied mycelium accordingly to this data. So here is just a series of these heterogeneous skins that I've 3D printed with the wood-based filament. And then the mycelium was inserted into this form accordingly. And as you can see here, these pathways were specifically created to really choreograph the growth of mycelium. And here you can see the mycelium eventually began to grow and degrade the entire structure. adopting its overall geometry. So here's the final result of the mycelium adopting its overall form. I'll just briefly run through this second project, just to close up the talk. So this project is entitled Biofeedback. So again, it's taking, again, thinking about how to really incorporate biological growth, robotic intervention, and computational form within a unified process. So here I began to think about how can we allow mycelium to become a co-creator within the design process. So how can we really trace around mycelium growth and allow that to dictate computational form? So through a process of edge detection, I began to trace around mycelium growth and extract its curvature, which really produced quite intricate and fibrous forms computationally. So even just scanning mycelium and allowing edge detection to trace over its form produced quite interesting set of drawings. Here's just another example of that drawing set. But then I began to think, okay, so here is the patterns that mycelium produces computationally, but how do I add my sense of design aesthetic to these mycelium-made geometries? So what is the fusion between the architect's design aesthetic and these mycelium intricate drawings? I then began to apply an additional algorithm to these drawings, which added a layer of complexity and organization to these drawings. So here's the final results of the algorithm applied to the mycelium drawings. Just some more examples of these. Then I began to produce quite a large catalog of this fusion between the architectural algorithm and the mycelium scans. So here's just an example of this fusion of the architect and biological growth, and then questioning how can they become co-creators within the design process. Just a few more forms of those. And then I began to 3D print these geometries with the industrial robots. And these were actually 3D printed with a mycelium-based medium. So this idea of 3D printing these geometries with the biological mycelium material. And then over time, these 3D printed extrusions began to grow and actually began to fruit mushrooms as well. I'm just going to end it there, because I think I'm a bit over time. But if you'd like to know more about my practice, feel free to follow me on biolab_studio on Instagram and visit our website at biolabstudio.com. Thanks, guys.
Thank you. Really interesting.
Thank you.
So maybe if you have time for the discussion, I'm pretty sure there will be questions from the audience. So we'll just try to get to it fast.
Yeah, Natalie, thank you very much. It was very inspirational. I have a lot of questions. So Happy New Year.
I'll try stick around.
And thank you for the audience needs to know that it's actually 1 o'clock in the morning right now. So thank you, Natalie. Yeah, next up is Benjamin. So Benjamin, if you want to share your screen.
One sec. Can you see that?
Yes.
Good. Okay, yeah, hello, and thank you for the opportunity to present here today. My name is Benjamin Kemper. I'm a doctoral student at ETH Zurich and Anhalt University of Applied Sciences. And I've started my PhD in April 2020, so quite fresh, with a research on multi-material properties of robotically deposited bio-based materials. I'm part of the Materiality Research Group in Dessau, and the research is supervised by Professor Dr. Overstadt from Zurich and Professor Dr. Kretzer from Dessau. And quick info about me. I've graduated from TU Delft with a master's degree in hyperbody robotic building in 2018. I've earned a bachelor's degree earlier in architecture as well, and at the Cologne University of Applied Sciences. And since then, I'm experimenting a lot with 3D printing, 7-axis robotic milling, cutting, and also printing, 3-axis CNC milling, laser cutting, so to say the full exploration of the digital fabrication field. Another research project I'm investigating in a fully computer generated and manufactured house, where I focus on usability and sustainability. I just want to quickly show you the master thesis. It was called Running Out of Gas on a Fast Lane. So in this hypothetical situation, offshore drilling rigs will need it to be repurposed. So it addresses the dangerous consequences of climate change, especially in the Netherlands. They're facing the rising sea levels and the loss of livable land due to flooding. So on the one hand, we need to research possibilities to slow down the process and also change our way of life. On the other hand, we must also look for concepts and design proposals to support a lifestyle with radical climate changes. So how are we going to live in the future, I ask myself, and which role will architecture play? And to me, it seems as a balancing act between a utopia and a dystopia. So this project especially showcased the possibilities and benefits of computational design on multiple layers. The design was developed with the use of data gained through analytic methods, agent-based modeling, differential growth, diffusion limited aggregation systems. They have to create an unconventional, however logical, schematic framework. And on a macro to micro scale, computational design strategies were combined with material computation and robotic manufacturing. You can see a extruder I developed to print 2 different types of silicon, and I did some prototypes for the project with it. And as a follow-up project that derived from the robotic printing system from this master project, it was the hybrid chair. And it demonstrates the integration of multiple robotic production methods and results in a novel multi-material system, symbiosis of hard and soft materials. And the compound of hard and soft is realized through developing and integrating of subtractive manufacturing and robotic 3D printing. You can see it in the next section of the video. Also, the toolpath was specialized for this printing method and the integration. This hybrid chair was developed by Sina Mostafafi, Daniel Fischer, and myself, and it presents a customized computational design to robotic fabrication workflow of a material system composed of subtractively produced EPS and additively manufactured silicon. Next up, this summer or last summer, we did a workshop also for DigitalFUTURES. Was called the High-Sci Hybrid Intelligence Sci Matters. And initially we designed 4 hybrid prototypes to show 4 different possible topological integrations between 2 matters. They were then printed in 3D and in 2 different colors, red and white. You can see it here. So from left to right, top to bottom, there's a penetration of A in B, gradient of A to B, and distribution of B on A, and intertwine of A and B. So it was a theoretical research of how to combine 2 materials. Then the participants were asked to design and prototype hybrid informed material systems, and the goal was to address the symbiosis between the human body and the environment. You can see some final outcomes. And here are some sections of multi-material prints of the designs of the participants. They used various strategies in Houdini and Grasshopper to computationally design these hybrid systems. Also, this workshop was supervised by Sina, Mostafafi, Adi Preis, and myself. So now about the real stuff, because we saw a lot silicon, EPS, plastic. This is a problem, and that I want to face in my research. So the last project showed computational system and strategies to achieve a hybrid material system, but using, as I said, petrol-based or at least hard to degradable materials. We are all aware by now that plastics are a massive problem to our planet. According to Samantha Staley, 100 million tons of plastic are consumed every year, while only less than 10% were recycled. Usually then the plastic products end up in the oceans and pollute our environment. This is a plastic recycle chart, and it shows the big 6 plastics we can recycle. The problem is here that it needs, first of all, to be recycled, as I said earlier, and the right recycling method needs to be chosen, which is not always a simple procedure. And there are biodegradable polymers, two types, the agropolymers that derive from biomass products, such as polysaccharides and proteins, and the biopolyesters that are produced from microorganisms, biotechnology, or fossil resources. PLA, as also heard earlier, is quite famous for 3D printing. It is biodegradable, yes, but only under the perfect circumstances and time. So in the end, the microplastics get back in the circle and harm us as human beings. That's why in my research, I am focusing on these polysaccharides, mainly on starch. I think starch is quite suitable. It's vegan, it's low in cost, and personally, I think it creates a promising bioplastic. So this just quickly the setup. So for the preparation of bioplastic, you don't need a lot of things. So here's an example with agar-agar and hemp. So you first cold mix the ingredients, then mix it on low heat and stir until the biopolymer swells. And this process is quite different from the standard plastic process because it's a physical and not a chemical one. So to compose bioplastic, you need a few ingredients. The biopolymers, that could be starch, xanthan gum, pectin, agar-agar, and so on. Bioplasticizer, such as glycerol or sorbitol, and a solvent. And then later on in the process, additives can be added to change the material properties, so, such as food waste, onion, banana peels, coffee grounds, or cellulose-based waste materials, hemp, or sawdust, wood, paper. And we saw it already in the introduction. There are already some projects done. The MIT mediated matter group in 2018 is quite interesting, and also the Mycelium project by Klarenbeck and Dross was very helpful for me in my research. However, at the bottom left, you can see the two pictures of the bioplastic robotic materialization project. And that was a starting point for me for my personal research at the Materiality Research Group in Dessau. This is my idea of the research. So I think the climate crisis has inspired the need to explore alternative opportunities for sustainable fabrication processes. So plant-based bioplastic have emerged as a potential part of a solution to quell the impact of climate change. The following research synthesizes cutting-edge fabrication tools such as robotics and biodegradable materials to create an eco-sensitive design that can support a realistic and optimistic human lifestyle. The possibility to digitally program properties of objects leads to a complex study stream that informs machines, tools, and the precise distribution of materials. Modifying these compositions of recipes and merging different materials together allows for programming a range of varying characteristics in one single object. So the gradients between soft and hard, porous and solid, or tensile and compressive, will enhance the design and material space. This is where I work. It's in Dessau, it's the Materiality Lab. And these experiments are conducted there. It's part of the RMIT University of Applied Science, of the design part of it. It's, as I said, supervised by Professor Dr. Manuel Kretzer. And yeah, on the left, you see a picture of our last workshop. And I want to show you what we did there. It was called the 3D Printing Bioplastic Workshop. And the goal was to arrive at a bioplastic composition that provides the right viscosity for LDM printing. That's liquid deposition modeling. It should dry fast enough to 3D print. It should have the ability not to collapse under its own weight. Should remain durable and tough after curing, and also have certain pleasing visual aspects. Before printing, with the actual setup, the liquid deposition modeling setup, the students were asked to do a series of small tests, and every student was experimenting with a different base recipe. So changing ratios and adding additives in the process for a better result and better characteristics of the material. And to compare it better and to determine the material behaviors, we provided a layout, and yeah, it more or less worked, let's say. And so these, if I go back and forth, these are the fresh pictures, and this after 3 weeks. And of course, the workshop was not 3 weeks long. We only had 1 week, so we therefore we needed to have some educated estimations about certain material characteristics, such as shrinking and molding. The setup we used is a WASP data printer and a LDM extrusion system. And here's a working time lapse of one of the compositions. Another key factor here was that we needed to consider was that the material properties needed to adapt to the extrusion system, because it works with high pressured air. It couldn't be too viscous or too fibrous, because then the material would not reach the end of the nozzle. Here's the actual speed of printing. However, we needed constantly to observe the feed and speed while printing. So sometimes it was faster, sometimes even slower, and it also depending on the mixture and the base recipe. These are the final outcomes. You can see already some worked, some didn't. We can see the right or the wrong viscosity in the lower left. It was just too fluid, and or above it was not going through the cartridge. And also in the middle, it collapsed under its own weight. So however, we adapted the two-path strategies, geometry, and G-code for better printing results. And this is after 3 weeks. You can see in some a huge difference, and some almost stayed the same. And so the main problem is curing and cracking and shrinking. So there are a lot of forces depending on the base recipe and molding, but I think I know it can be solved with a serious sterilization of the base material. So just want to finish with a few close-up shots. So this one is a starch-based bioplastic. It's a combination with hemp shives. It had, you saw the time lapse, it had perfect printing properties. However, a strong shrinkage while curing, and therefore this cracking. This one is xanthan-based, and it's combined with eggshell powder and coffee grounds. There's no shrinkage at all, and it has reasonable printing abilities. However, you always get one property, and it's like cement. It's always hard, and it molds after some time. And the last two ones are agar-agar based. This one is colored with a beetroot juice, and they are also quite good to print. But there's this one collapsed, and there's this strong shrinkage, and it molds like pretty ugly after a short time. So this is where I am right now. I want to, as I described earlier, combine these with a robotic printing setup and this multi-mode, multi-material printing, but still, therefore, I'm at finding out how to get the a good material that I then later on can change on the run with a robotic setup, and then later on in the process create architecture or prototypes and designs out of it. So that's it. Thank you.
Thank you very much. Fascinating. Thank you. So now we have, next up is Jessica.
Can you hear me?
Yes.
I'm going to share my screen. So you can see my screen now?
Yes, perfectly. Thank you.
Hello, everyone. My name is Jessica Mendes. I'm a Mexican architect, and I hold a master degree in advanced architecture by IAC in Barcelona, where I was part of the research group Computation by Materials and Architecture, tutored by Professor Marcos Cruz. Since then, I've been teaching in researching now here in Mexico, the integration of microorganisms, biomaterials, and environmental performance in architecture through computational design and novel fabrication strategies. Today, I'm going to present the project Bioactive Ceramics, which focuses on the development of passive biofiltration systems applied on architectural elements. So I would like to start the presentation with a quote by Lela Rembrandt, who in 1993 said that one of the legacies of the Renaissance is a tendency to think of buildings primarily or initially as objects of artistic or social significance, but not as objects operating within the environment. And I think these limitations still exist nowadays. I think one of the challenges for new generation of architects is to overcome this legacy and really think of architecture as objects of environmental relevance, that they can give something or exchange something with the environment. So following this thought with some students, we were wondering how we can contribute to solve a problem that many cities around the world are facing nowadays, which is air pollution, and how we can do it from our position as architects. So together with the students, we started looking at techniques or already existing processes which are using living matter in order to clean or degrade polluted air. And we found out that a very common process used in an industrial scale is biofiltration. Biofiltration is a technique to degrade pollutants using living matter. And in this case, we focus on open systems, given that we were interested on exploring how could we apply this into architectural elements open to the environment, which means that we will have a controlled environment for the microorganisms to live. So the first thing that we did was to analyze which are the main components of a biofilter. First, we have to know which pollutants we're interested on to degrade. And in this case, we focus on VOCs, given that they are very common pollutants like around the world. Second of all, we have to find which microorganisms are able to degrade these pollutants. After this, we have to define a medium material in order for microorganism to be host in this material. And finally, we have to look at the environmental conditions in order to be able to control them, to be able to keep the microorganism alive. So after we defined we wanted to work with VOCs, we did a bacteria selection process. We were looking at some parameters we wanted to find, or characteristics we wanted to find in a species, and we analyzed 4 species. And we found out at the end of the selection process that Bacillus subtilis was a really interesting species, given that it's really easy to find. It's non-pathogenic, easy to handle, and it has a mesophilic characteristic, which means that it can survive in extreme temperatures, especially high temperatures. So after defining the bacteria and the pollutants we wanted to degrade, we also defined that we wanted to find this bacteria naturally. So we did a bacteria isolation process in which we collected 2 samples from some areas outside the school. And we got 1 sample from decorative grass soil, a 2nd sample from wild vegetation soil. And after a series of tests, bacteria culture, species differentiation, strain differentiation, and purification process, we obtained our Bacillus subtilis bacteria from the wild vegetation soil. And This was because the decorative grass soil usually has a lot of fertilizer, so this doesn't allow for more species to be part of the soil. So after this process, we obtained naturally the species we were looking for. And right after this, or parallelly actually, we started looking at the medium material we were interested on working on, which was ceramics. Ceramics, it's already used in biofiltration processes. It's a very common material in an industrial scale, and also is a widely used material in architecture. So it was the perfect material to use as medium for the bacteria to grow. And the most interesting thing was that we worked together with the industry in order to get a proper mixture material to create the perfect environment for the bacteria to grow. So we analyzed some of the most common aggregates they used for ceramics. In this case, the industry, what it's looking for is to have less porosity and actually not allowing bacteria to grow. But in this case, we wanted to do the complete opposite. So we were looking for a lot of porosity and to find the proper pH scale so the bacteria could grow properly. And at the end of the test, we found out that calcium carbonate was the aggregate that was giving us the proper conditions for the ceramic to host the bacteria. After this, we did some inoculation process on the ceramic mixture. We also did some morphology tests to see which kind of width and depth bacteria like the most in these ceramic pieces. And right after this, we started developing the design proposal, which at the end was a drop-like ceramic component, which was having this tunnel right in the middle, following the Bernoulli principle, in order to control the wind flow. In this tunnel, we will be placing the bacteria. And at the top part of this tunnel, we were also integrating the texture in which the bacteria will be hosted, in order as well to control the wind flow so the bacteria wouldn't desiccate, because all the wind that will be passing through this tunnel. For the overall geometry, we were looking for a self-supporting system to have some structural stability. At the end, we also run some environmental simulations in order to integrate some design inputs from these simulations. We were looking at temperature control, given the context in which we are, it's really high temperatures. So we wouldn't want for the bacteria to get the complete exposure to sunlight. So we were locating the bacteria at the top part of this tunnel. We also have some wind flow simulation, and watering channel, which was really important in order to keep the bacteria alive. Like, we need to keep moisture in the piece. We run also some environmental simulations, sun exposure simulations, because as we have quite high temperatures, it was really important for us to know that the bacteria wouldn't desiccate, or that the sun would actually dry all the water out from the piece. We designed some assembly system in which we defined 3 different pieces with some details that will allow one piece to stack on top of another. So another really important part of the process was the prototyping and the fabrication of the process. And it was also really interesting, the process, to partner with the industry in order to mass produce these pieces. The process for the mold making and the casting and the glazing part of the piece was really interesting. It was quite a challenge. We built a mold made out of 8 or 9 pieces, but at the end it was really easy to assemble and disassemble this mold, and we managed to produce around 70 to 100 pieces. And we also defined the area in which we want the bacteria to stay using this glazing technique for the ceramic. So as you can see in the center, we have this ceramic natural, or ceramic natural, and around this area we have the white glazing, which will limit the bacteria, let's say, invasion of the piece. Here we have a test on the assembly part of the prototype. And finally, we ended up with this column-like installation made out of ceramic components, can stack one on top of another, inoculated with bacteria able to degrade VOCs. So the presentation finishes here. And I would just like to mention that some important steps that are coming for this project is actually testing it outside the environment, and which is the relation of these pieces in the environment, and not also with environmental conditions, but also with some other species that will for sure invade this prototype and these pieces, not only microorganisms, but also probably some small species like spiders or ants or some bugs. So we're really excited to see what's the evolution and the relation of this installation throughout the time. Thank you very much.
Thank you so much. That was really inspiring. Thank you. And I'm pretty sure we'll come back to some of these topics that you talked about in the discussion. So thank you. And just a reminder to the audience, if you want to ask questions, please go to the Digital Futures live stream on YouTube and ask your questions there, and we'll address them. We'll ask the presenters to answer the questions in the discussion part. And now we're moving actually on to the next presenter. We have 2 more presenters. So I would like to ask Joanna to share her screen. Joanna, are you here?
Yes, I'm here. Hello, everyone. Can you hear me?
Yes, perfectly.
Thank you for having me. My name is Joanna Maria Lesna, and I come from Poland, where I graduated from my bachelor, and currently I'm in Tokyo, in Japan, working as an architect at Kengo Kuma office. I'm going to present today a project which I started to develop on my master thesis project at CETA Studio at the Royal Danish Academy of Fine Arts 1.5 years ago. And the project is about the digital design and fabrication of algae and fungi-based biopolymers in a holistic approach based on the studies of the material properties and its post-fabrication behavior. The project's first assumption was to create a shelter which disappears after the seasonal use. In the past, humans have created structures which were assumed to be everlasting, while temporary architecture is most often associated with the ease of disassembly and transportation using prefabricated and standardized modular components. Materials and architecture components intended to be disassembled and reused following the circular economy and sustainable concept of closed life cycle. However, the waste management is currently a huge concern in the construction industry, and the materials which were intended to be reused ending up anyway on the landfill side. Building construction and manufacturing industry consume 40% of the total amount of raw materials needed in the global economy, and those materials such as sand and minerals are finite. So the idea of the research was to look for material which the planet could regenerate and grow. And here, the environmental crisis and the problem of the white pollution encourage researchers to investigate sustainable materials. And these are inter alia biopolymers. The biodegradable bioplastics or biopolymers are made from renewable biomass sources. Those are polysaccharides, proteins, and lipids, which are found in the cells of living organisms. They are renewable, biocompatible, and environmentally friendly ingredients. This is cellulose, starch, chitosan, seaweed such as alginate, carrageen, or agar. Due to the biological origin of the biopolymers, they are biodegradable, which means they are easily broken down in the natural environment into carbon dioxide, water, energy, and cell mass with the aid of microbes. And the best thing is that the biopolymers can be reproduced anywhere without special facilities. Natural biopolymers are already in use by designers. Those are very well-known designs, examples of industrial design, fashion, furniture, or installations. The main focus I put on the chitosan in this project because this material is not only biodegradable, but it is used as a soil amendment in agriculture, giving a great benefit to many plant species. Ironically, the agriculture sector plays also an essential role in the plastic waste production. Agriculture widely utilizes plastic products, especially plastic films, in a form of tunnel or greenhouses for crop protection, shading, and temperature enhancement. This phenomenon has been even defined as a plasticulture. So main concept of the project was that if the life cycle of the products begins with the biodegradable materials, one doesn't need to concern about potential recycling. Moreover, the matter of the objects could be recycled not by saving the material, but by commanding the objects to decompose into programmed particles or components that then can be reused to perform new functions. Within an agriculture context, this implies structural life cycles that, after the seasonal use, return to nature and enrich the soil to grow their raw resources and use them again as a building material. The primary goal of the research employed an integration of the design process from the ground up by synthesizing material creation, digital modeling, and robotic fabrication and assembly in a holistic way. Modern human-made structures are inefficient when compared to nature, which creates complex, dynamic structure with functionally graded material properties. New tools like computer-aided design and robotic fabrication are enabling us to create such a complex objects. This I tried to achieve by multi-scale modeling approach. The design problem is decomposed into distinct but interdependent models according to the scales, and data is transferred between those models. It contains three scales: material design, pattern, and the form. The key challenge of the investigation was to integrate material composition and behavior with the digital modeling and fabrication in a way that the form generation is driven by maximal performance with minimal resources through the local material property variation and the material grading by transparency and structure performance. The research was initiated by an empirical experimentation of the material search. Fungal chitosan, agar-agar, and sodium alginate were mixed with water, acetic acid, and other additives in various proportions. It is quite similar process of creating a biopolymer as previously Benjamin was presented. By changing the proportion of the particular ingredients, material samples result in diverse properties like color, transparency, tensile strength and elasticity. The material samples were tested using a universal testing machine to test the tensile strength and elongation. The best results show probe which consists of 12% of chitosan. However, elongation of the sample achieved only 2%. Adding 5% to the mixture improves ductility of the material and at the same time reducing significantly tensile strength. The transparency was tested in the light chamber with a luxmeter, and the emission of the light through the samples varies from 67 to 1,120 lux. The global shape of architectural membrane was found using a physics engine in mind to be reminiscent of typical membranes used on farmlands. The membrane was divided into the elements to simplify the assembling process. The elements were further generated by clustering the mesh points using the Kamin clustering method. The elements were further partitioned using the algorithm that the edges were subsequently relaxed and developed into a specific pattern of customized panels for the sake of fabrication and assemblage. The functionality of the materials implemented in the system was investigated in two main directions, structure and light. That was the structure performance of the global form and solar radiation on the specific site were computationally simulated. The third direction is that the gradient of the transparent on the bottom through yellow and red on the highest position on the structure was determined by agricultural purpose of the membrane, where red is considered as a color which attracts insects. Functionally graded materials are those whose properties can be adjusted accurately and continuously and tailored to their particular use. The aim was to create a system that gradually varies its functionality by varying the properties to achieve an optimization of the structural performance of a tensile structure, decrease the solar radiation and gradation of the color of the material depending on the height of the structure. The gradation of the material properties, which is rigid and pliable, transparent and solid or colorful, heavy and lightweight, is possible by combining the components with a particular property in various proportions. This variability of the material distribution aims to create a complex and multifunctional body. Grading the material was obtained by generating distinct layers for specific functions. So the 3 layers of the customized patterns were generated for each of the panel. The first layer acts as a membrane and is specified by a distance to the ground. The upper panels are red, and the closer to the ground, the more yellow, white, and transparent the material becomes. The material grading on this level was achieved by creating one material composition per one panel. The composition was adjusted by changing the components agar-agar, chitosan, and sodium alginate in order to reach desired color and transparency. Additionally, the area of the edges contains small glycerin, which makes the material more flexible in order to enable sewing to assemble the panels together. The next layer consists of load-bearing pattern informed by the simulation of the structure behavior. Points on the mesh of the panels were grouped by the Kamin clustering method by the distance to the edges and structure behavior. On this base, a branching pattern with varying width was generated. Prior to the visual pattern, there was created a database which informs the robot about material composition. Chitosan here differs between ratio 9 and 16% and agar-agar 2 to 6. The higher the ratio of the both ingredient is, the stronger and heavier the pattern is. The final pattern is responsible for the solar radiation protection. Therefore, the pattern of this layer was created by grouping areas of similar radiation results of the simulation. For each of the areas, random points were generated with various density and connected with the shortest path. In this way, the created pattern was denser for the areas with the highest radiation results. As in the previous layers, prior to the pattern generation, the data for fabrication process was created. The material was extruded in the liquid form through custom-made extrusion system using robotic arm to determine gradient in material deposition. It was crucial to investigate material composition, material concentration, and the pressure variation, what results in varying material accumulation and layering. Working with the multiple material properties of functionally graded structures requires adjustable deposition setup. Because of multiple material compositions with various properties, defining the deposition setup, flow control, speed and pressure needed to be considered. This was solved by testing chosen material compositions and applying an adjustable flow configuration for each of them. The intermolecular attractions of the particles in the wet water-based material allowed to create a continuous graded system of heterogeneous performance, which would not be able to achieve using other fabrication methods. The viscosity of the materials allows also for total self-bonding and self-repair of the layers in the print. The fabrication process of creating a material from the ground up and deposition in a viscous state required properly controlled environment and the process set up in terms of production. Because of the viscosity of the material, after extruding each layer, the following panels need to be cured in an air pressure box, which I built on my own. And they were cured in 40 Celsius degree to obtain quasi-solid state. The wet deposition of the biopolymer are under internal directional evaporation stresses while drying. This means it is very important to control the environment of the extruded artifacts while the evaporating process. After the panels were dried, they were assembled by sewing them together. This is an image of partly built pavilion exhibit at the Royal Danish Academy of Fine Arts 1.5 years ago. Future investigation of the projects would probably involve testing the material in the external environment. And an early integration of the performance parameters and fabrication methods into the workflow may produce an integrated design process. It is an example of conceptual and methodological framework of material-based design to fabrication process, which implements customized biopolymer design for the real-world application. It shows a strategy of rethinking the materials and the fabrication methods. Thank you very much for your attention.
Thank you so much. That was really amazing. Thank you. And now we have our last presenter today. Yunin, can you share your screen?
Yeah, of course. One sec. Okay.
And again, a brief reminder, ask questions in the chat, in the YouTube chat, and we'll address them after this presentation.
Can you hear me?
Yes, perfectly. Thank you.
Yes.
Okay. Sorry. Okay. Hi, everyone. I'm Yuning Chen. I'm from China. My presentation today is Biodesign Interfacing Nature. I'm a design engineer studying innovation design engineering in the Royal College of Art and Imperial College London. My background is environmental science. Working with nature is my inherent passion. I've always wanted to become the mediator between human and the living system. My main area of practice in biodesign is focusing on using design to mediate meaningful interactions and mutualistic relationship across different species and environmental entities. I'm very interested in ecological personhood, multi-species ethnography, and kinship building. One of my favorite quotes is that environmental crises are material problems with ideological roots. So biodesign for me is a tool to bring in the perspectives of the significant otherness, provoke public ecological discourse, generating conversations and actions that advocates ecological literacy and citizenship. I'll be sharing one of my recent biodesign practice, Project Habitats. Although I'm very interested in creating digital interfaces for the non-human, today we're talking about humans as the interface for the living system. This is an experimentation on redefining humans' capability to provide ecological services. We designed a living world that enable people to become the host for endangered organisms, which in return gives them a sense of companionship and belonging, breaking the cycle of conservation and destruction by creating a pattern of human-nature coexistence. The project originated from looking at the concept of ecological service, a metric that's used to quantify the contribution of every species to the stability and thriving of their ecological system, which makes us to question the ecological service that humans provide. After colonizing so many resources and niches, we're not giving back the ecological service accordingly. What if humans can serve back to nature? What if we can expand our capability of providing ecological services? During our investigation, we came across this cascading extinction crisis starting from ash dieback, a disease that's eradicating 80% of the ash tree population in Europe. Fortunately, the ash tree won't be gone forever, but the new population will take decades to grow. In the intervening years, hundreds of species of mosses, lichens, and fungi are risking secondary extinction, yet they're not getting the attention they deserved. There is no known conservation scheme protecting them. This is a silent apocalypse due to ignorance and irrelevance. Traditional conservation methods for these unassuming species can't cope with this scale of habitat loss. To thrive and reproduce, the species need a specialized substrate and access to a diverse population. What happens? Sorry. In the ethnographical study to understand and mycologists, we identify key requirements in recreating habitat capacity and bark texture, as well as connectivity. The slight high alkalinity of ash tree bark is one of the key features that supports a variety of gas species. After testing different materials, we found that plaster naturally has a similar pH to ash bark and is suitable for texturing. Tree bark's ability to hold moisture is vital for gas species survival. We tried a new technique from creating porous clay, adding natural foam in the casting process to generate different level of porosity and pick the most aligned one to the ash tree attributes. We also sampled the bark at both macro and micro level to understand the species requirement for bark texture, both in vivo or encountering artificial biomaterials surface. Cell responds differently to the homogeneity of surface spatial patterning at the microstructures from ash tree bark, and we took EMI to compare the morphology between our material and the bark, as well as making cultivation tests to see if the cell can acclimatize to the material surface. After creating 3 material-based factors, we started to look at the requirements of environmental factors, which are habitat connectivity and light intensity. Ash tree bark naturally structure and loose canopy, which attracted a range. We measured the index on the ash tree, one of the most important factors related to a healthy level of genetic diversity and population. Frequent normally provided by forests. During our research, we found that increasing mobility of hosts can significantly reduce the amount of habitat needed in relation to spatial areas, because it higher the interaction frequency. After understanding the need of our target species, we found that the most suitable role of human beings in the species, with movement and mobility of humans, they can be manifesting ecological and cultural. So we started to map the bioreceptive areas on human body, which is after also considering economics. We ended up focusing on the areas of risk to ensure the optimal light intensity for species survival. We also substrate to make sure it reached the light level as ash tree has. After that, we ran a modeling based on spore dispersal rates, population, and residents interact where the habitat is around once a week by an initial population of 5%. And this is the final outcome of our wearables that augment the bioreceptiveness of human body and enable everyone to become a host for the endangered species. In an era of social distancing, the living wearables can be a vibrant indicator of ecological social connectivity, reminding us that no species is an island. This is a beginning for me to answer the question of which beings flourish, which fail when natural. One of my biggest reflections after this project is that human perspective in biodesign projects is actually quite easy to be neglected, despite designer being human, which makes these projects into a reality. It's intriguing to think about how humans are interfacing nature. Are we virus? Are we monster? Are we just a grain of dust? How can we better ourselves from the perspective of the otherness? Or maybe we could never find out. After all, we're all lichens. Thank you.
Thank you so much. That was really interesting. Unfortunately, we couldn't hear a few of the words. So if the audience, wants to ask clarification questions or the other speakers want to, ask questions, please do so. And now we want to open it up to the discussion. So all the speakers that are still awake, please join us for the discussion. I know a few of you are in areas where it's already very late. So if you can't make it to the discussion, that's okay. But yes, so Gustavo, did you want to start off with a few questions?
Well, I guess I just wanted to thank everyone who presented today. And I just wanted to really say that there were a lot of provocations, a lot of great work, but a lot of provocations that were posed in these projects. And I think one of the core questions that I wanted to ask off the bat is maybe we're coming at this as researchers, but you guys are the future. You are the thought leaders of the future. How do we change the politics, the academic system or the professional system to make your research more robust, to make more permanent change in society? I think I wanted to start out with, how do we move forward? Anyone?
So, yeah, the question basically like, what are the obstacles, but what also are potentials that you see? And how would you like to see your projects be implemented, not only in the real world, but also in academics and thought. So maybe Jessica, since you talked about it with your students, what is your vision? What would you like to see your project grow into? And what are the academic goals for you maybe with your research?
Well, for sure, I think one of the challenges is to to make the students know about the importance of the integration of nature into our field. I think since a long time ago, we integrate, let's say, the environmental conditions, and we look at nature and we consider what we were able to see, but we have never considered what we are not able to see. Now with technology, we are aware that many other species exist, and the relevance to the environment and to many other things with our own existence. Now we know about them, and I think it's really important to be able to integrate them in a way in design, in architecture in general. I think definitely one of the obstacles is timing, because when you're talking about the integration of nature in any aspect of our lives, I think nature works at a very different time pace. So I think this is a really big challenge for us, how to deal with time between our time pace and nature time pace, because we are so used to the immediacy of a click and to see that something is happening when you click something, and in nature, it works at a very different scale and a very different timing. So that I think definitely that's one of the obstacles. And another obstacle, I think I wouldn't say it as an obstacle, but maybe it's an opportunity to work together with the industry. I think it's essential part of how this can have more impact in our daily lives, definitely. That's why, I mean, most of the projects I've developed, I've always looked for someone who's interested on giving a bit of input from an industrial point of view in order to integrate this in the project, because I think it's essential to work together with them. At the end, they're the ones setting the steps of what's going to arrive, let's say, to the general public or to our daily lives in general.
Thank you. Yeah.
One last thing I would like to mention as an opportunity, I think it's to consider biodiversity as well in design, because for so long we've been focused on our species. And I think in this last, let's say, 20, 30 years, we've been opening our minds, looking at some other species, but we're still looking at a very small section of nature, let's say. And I think design for biodiversity, it's a great opportunity to develop our work further, definitely.
I just wanted to interrupt. Thank you very much, Jessica. But I think, Victoria, didn't Joaquin put up a slide that 50% or 60% of the biomass has disappeared? So,
yeah.
so in the last 50 years, we have seen a shift in biodiversity, even just sounds and just our environment are impacted, less animals. I mean, Benjamin, what do you see as a thought leader here? So if you had like all this, drive and budget, how could you help fix or steer the ship?
Yeah, it's a good question. I'm not sure. I think it's at first about awareness, of course. I mean, it's a big buzzword. I can't hear it anymore, but it's about that. And I don't know, maybe right now is actually the right time. So if we would have a lot of money and our budget wouldn't matter, maybe right now people get the sense that we are treating the earth in the wrong way. So my hope is there that it's actually the right time for a paradigm shift. And I think we need to clarify somehow that it's also, if you work with the mycelium and so on, it's nothing disgusting we are working on, but it has a certain beauty itself. So also I think the trick is here not to mimic what we've used to, but the material itself will design, or will shape the outcome, and we will get used to different objects and things. Yeah.
Yeah, very interesting. I think like this kind of feedback, Natalie was talking about that too, right? The biofeedback to kind of like choreograph almost the actions of the microorganisms that you're working with. So I think one of my questions would be how has it been for you, because you all of you are designing at different scales. You're moving very fluently from the micro to the macro, and you're developing your projects at multiple scales, not only the spatial scale but also the time scale. As you mentioned, Benjamin, you're designing with microorganisms that work differently, right? So maybe you can talk a little bit about the process and what you've learned moving between different scales from the lab to, you know, testing it out and then working with the organisms and the different time rhythms and scales. How has that been, or what have you learned?
I think the main thing is that it's almost never linear, so you just cannot scale it up. In the way you test it on a micro level, it behaves different on a meso level, and it behaves again different on a macro scale. So yeah, this basically it. I think it's yeah. I mean, to be honest, I'm pretty much at the beginning still, so still figuring out. I have ideas what to design with that. However, as I showed, I had like these 3 columns of my research. It's also the technology what I'm interested in. So maybe to clarify that's why I also showed all the bad materials and the projects with it in the beginning, because it's there I consider the material as placeholders. So moving forward, I think we now have the opportunities to use robots, to use drones, to use 3D scanning, everything, and then we should take advantage of using these technologies with biomaterials.
Great. Yes, thank you. Did any of the other speakers want to join and turn on their cameras?
Yep.
Whoever's still here,
I
please
think
join
Natalie
us.
wanted to say something.
Yes.
Yeah, and Joanna too.
Thanks, Gustavo. Yeah, I just wanted to touch on the point of you know, academic research and this connection to, you know, real world architecture. It is a quite interesting topic because you know, I studied this, you know, I gained skills such as many architectural students of, you know, computational design, robotic fabrication, really innovative techniques within university. But once you get into the real world of architecture, you know, your role is basically just to design bathroom layouts, you know, and apartment buildings. And I definitely feel that there's a disconnect between, you know, academia and the real world of architecture within the corporate field. So it is quite interesting is how do we now bridge this research of biological design to the real world, and you know, not just create exhibitions and small scale designs, but really apply this to architectural scale buildings. And it is quite difficult, I have to say, you know, capturing these characteristics that happen on the micro scale and apply them to the architectural macro scale. So it will be quite interesting to see, you know, how this next generation tackles biodesign and applies it to real world architectural buildings, because I think that is the missing key link within biodesign.
No, Natalie, yeah. I wanted to say you make a great point. I think in my PhD studies, if you look at the literature, there are designs and a treatise that actually talk about, you know, biodesign, morphogenesis through the generations, it looks like. So the bigger question is, have we not had the will? Like, is it about why do we learn why do you learn robotics and then go and make you know, a square room or an apartment building that is maximized for industry and budget? Isn't architecture's role to challenge our imaginations and to really push for a better society. At least that's what I was implanted as a young scholar in architecture. Natalie, do you want to respond to that? Or any other of the panelists?
Maybe also Jessica, because she was talking about the industry. So Natalie, but I want to give you the word.
Yeah, I completely agree with that point. You know, once you graduate from your architectural master's degree, especially if you go to universities where they really push digital fabrication, computational design, when you get to the real world of architecture, it's like, wait, where are the robots? Where is the grasshopper algorithms? Why aren't we creating these crazy forms in Maya? Obviously, you have these outstanding architecture firms like Zaha Hadid and other firms like that, but majority of the architecture firms are still stuck in these banal ways of thinking. So it is an interesting point of how to transfer these skills of, by design and computational design and apply them to real world of architecture. So I definitely agree with that. There is a missing key link.
Joanna, do you want to respond to any of what we talked about or say something about your vision of the future or how we can make things better?
Yes, I think the most difficult is the connecting industry and academia research is that the research didn't test like the biomaterial used in architecture so well, like in the large scale design. And that, I guess, what industry is afraid of, especially about like the post-fabrication behavior of the material and the external use. Like, can we put the mycelium or the biopolymer outside, like in the external environment? Like, we don't know what's going to happen in that, like in a few years. So I think this is just a field which wasn't researched too well, I guess.
Yeah, I think it's an interesting point that you're making, that there's arbitrary lines that are drawn, and then there's a certain hesitancy of the industry or general public to move across that, because we have that illusion of cleanliness when it comes to bacteria or microorganisms, but the illusion of that is crazy because we are basically surrounded by it at all times, right? If you think about, like, even your cleanest house has a lot of microorganisms in them. And I think, yeah, what Benjamin said earlier, the awareness, creating awareness, I also don't like the buzzword awareness, but I think in this case, really educating people, and the work that all of you do is amazing, because you're not only pushing your research forward, you're also sharing it with others and are educating people about it. So I wanted to ask Jessica again to maybe give us a little bit of insight how it was for her to work with industry leaders together with your educational, research lab. What was the response, or how was working with industry in that sense? Because I think a lot of them have a lot of, knowledge discrepancy. They may not know what you wanted to achieve with this. How was working with industry leaders for you?
Well, actually, it wasn't that difficult, because we were actually working with the people which was there 8 hours a day, working with the molds and working with ceramics and working with all of these things. And for them, it wasn't different than working with what they do every day. So with leading partners, I think the most important thing is to really sit with them and explain them what the project is about and what can lead to, and showing of some examples on how it's been done in other areas or some other industry that is able to actually open their minds and open their installations and giving you some help on developing the work. And for us, it wasn't that hard. And I think it's about going there, knocking at the door and try. I mean, for us at least, it was like this, and they were really helpful. Without their experience, we wouldn't manage to solve the project, especially the part of the fabrication process and taking it into in a big scale. Without their 30 years expertise, we wouldn't be able to get the project done, definitely.
Yes, Jessica, you bring in that is a really good point. I mean, sometimes it's hard to imagine when you're, I remember being a young student and seeing all these great professors going, you know what, you can take over the world and do anything, but unless you start with people that have knowledge, creating good relationships, and really just striving to show your own artistic and research integrity, there's a bond of trust there. And it seems as though that I'm not sure if the profession or society has lost their bond of trust with architecture, or is it about the idea of contractors being confused with architecture. But I understand that in the field of architecture, we want to strive for better. We want to push and move society forward. Jessica, I wanted to ask you another question. In where you are located, how does the field look like for what you do? Like, are there buildings that are embracing biodesign? Is it more, what percentage is it? Is it 1%, 0.1%? Like what do you see?
Well, unfortunately, for the Latin American context, and especially in Mexico, we're so behind so many other topics around making our cities a safe place to live, have a proper and housing system, etc. That biodesign is not actually part of the discussion nowadays. So actually having this opportunity to be in here talking to you, showing what we're doing, it's really important for us, because it's the only place in which we can actually talk about what we're doing from here. No?
Benjamin, I just wanted to ask you briefly, in where you are located in your geography, can you report back to kind of us? What do you see? How do you see biodesign taking a place in culture? Is it a lot? Is it 50% of the population have buildings and furniture and objects, or is it just a few? Can you please comment?
Yeah, I would say it's just a few, and because I think, I mean, on the one hand, you have the industry, as we discussed, and it's hard to change that huge building industry with concrete and windows and everything. And at the same time, the people get used to that. If you look at houses and compare it to cars or whatever, it's always the same. It's a square room, a door, a window, a roof, and of course. Back then there was a little more ornament and so on, so the style changes a little bit, but that's it. So the biodesign is pretty radical change, I would say. So I think on the one hand we need this education we were talking about, but also we need maybe restrictions in a positive way, because if we know that the plastics we use in buildings are not good for the environment. We know that the concrete produced a lot of the global warming and so on, but we still use it. We still go on. So if we allow more research in our field, that would help to get a faster change. So to answer your question, I think I don't see a lot of biodesigns here.
Yeah, I think.
No,
sorry,
Victoria. No. Can you comment too? Hey, since you've actually put together these two panels, and you also do biodesign and eco-design in your work, can you please comment about what you see and how the field can push forward? And the next question would be for Joanna as well.
Okay. Yeah, I think what I especially learned also from the last panel, just to advertise again, like watch this panel was really great with well-renowned leaders of the field. The interesting thing is that most of the solutions are very close to our already known systems, and there are small changes that can make a lot of difference in the world. But the thing is that, you know, it's about the storytelling in a way, right? Like Mitchell Joachim was basically showing us projects that were very innovative, but they were also using quite simple solutions to problems in our current environment, and basically showing people that through small changes, of course, we need to innovate, but also small changes and small steps already go a very long way. And then what Jessica said, to basically approach, you know, the industry that is often not even opposed to, is just not aware of, actually makes a big difference. And I think these small steps that everyone takes are already a big step forward. So to me, in my work and in my research, I think the small steps that are to pay attention are already like a big step, because you might be aware of it, but maybe the person that you speak to is not aware of it. So kind of creating that that bridge and educating people. What Benjamin said, the education part, I think is a big issue. And just also try. I mean, Sina just put in the chat here, which is not for everyone to see, unfortunately, that Philip Morel actually said in one of our panels that design research equals design experimentation and entrepreneurship. And I think that entrepreneurship, that kind of daring audacity to do stuff and approach people and talk to people, I think that is, you know, some people might think that's an activist approach, but I would say it's actually the entrepreneur approach, because we are still in an capitalist kind of system. So I think going out and actually talking to people and trying to get stuff done is the most important stuff that you can do.
Sure.
And I think all of our speakers have shown that in magnificent ways. So.
Victoria, I wanted to also jump in real quickly. Yeah, it seems as though that we are, there is a disconnect between academia and industry. In industry, I mean, at least when I was a younger practicing architectural designer, the hustle was a part of it. Like basically, if you were in a firm, you were okay making bathrooms and stairs and, you know, rooms. But if you wanted to be on your own and do your design, you were either stressed to pay your employees, yourself, and just even make the car work. So I think that the hustle is important, and also being an activist, but it's been so long. I mean, why aren't we driving? Why are the people not seeing the importance of having a balance between nature and our society? I think I'm struggling with, I see so many beautiful things, but then I go, why aren't we loving it and embracing it more? Joanna, did you want to say something about, you know, how you would be able to change, or how do you see things in biodesign in your world?
Yeah, unfortunately, in the industry, it's ruled by the clients. So if you work with the clients, which they mostly focus on the costs, that's the issue, I think. But also some of the clients it also depends on which person are you talking to, because some of the clients might be really interested, but really, as Victoria said, they're just not aware of that. So it's very important to just inform about the new research the academia is doing, and because mostly if the developer or the client is just comfortable with the conventional solutions, they just stick to this. But we really need to show the new tools, the new materials, and I think that's our role of an architect.
I was about to say, you know, Neil had a really good book about space architecture a while back, and we had a really good panel about it. Every time I see space architecture, I see biodesign, I see biomimicry, I see the future. And it's very strange that we look up in the sky and we see the future, but here on Earth, we just see this environment that's very, that doesn't enliven the soul unless you go walking into nature yourself. I think Jessica, Benjamin, or Yuning or Natalie, do you guys want to respond on how we can move things forward? Or if you have any questions amongst yourselves too, because you guys are the future of your fields, you know, directors of your own, you know, university programs in the future. What do you want to say to each other?
I can share some of my struggles. Sorry about my network. I think a lot of times we're thinking about biodesigns, biotechnology, around the topics of materials and making the cities more bioreceptive. And I think also, although we're trying so hard to increase the proximity between human and nature, I think there's still a lack of meaningful interaction between us and nature. We are mainly looking at a sensational interaction, not necessarily. It seems like we are losing the ability to create place-based knowledge and create real emotional connections with nature, even though they are next to our house. And that's what I've been like interested in, how to create meaningful narratives and relationship between human and the non-human.
Thank you. Yeah, I thought it was really interesting that you were talking about basically the human not outside of nature, but as part of nature and basically as a transmitter for information. There's this interesting quote that I wanted to share. Kevin Kelly in his book Out of Control is basically talking about the biological and the technological not being separate, because they are all based on informational systems. So he's basically envisioning a time, and that's very radical and very you know, provocant to say that there's going to be a time where there's no difference between the made and the born. And your project was showing, you know, all these different ways of interacting between species, but also integrating. And all of you show that technology is not negating that. So I think, you know, bridging and creating new narratives is very important and very interesting. So thank you, Yunan. And I didn't want to cut this off. So Natalie or Joanna or Benjamin, did you want to respond and kind of share some of your experiences or ask each other questions?
Yeah, don't be shy here.
Just maybe two things that come to my mind. So one thing was the references we all shared. They were pretty much only a few, and that just shows that that there's a lot more to come, I think. And I think 1940 something or so, Henry Ford designed the soybean car thingy. So that's how long? Yeah, it's 80 years, right? Ago. So, and we're still talking about this, and there wasn't happening a lot in the last years. So I think it's now is the time, and that just came to my mind. It's kind of sad that if people would have recognized the benefit of a different material back then, and that maybe the lobby behind it or whatever, or it would have been accepted by the people, we would be now at another stage.
I just wanted to jump in briefly just to say that if there's not enough books or enough articles or movies that actually show what the power of biodesign or eco-design, then is it our responsibility to publish? Is it our responsibility to exhibit or curate or to make movies or music? Like, what is our responsibility as makers and as researchers to put out the message?
I would say publish. I think the work that we do is very interesting, and I think people outside the field of biodesign are very curious. So I would say, you know, publishing papers, Instagram, getting the work out there to really spread this idea of incorporating nature, or this new relationship with nature and architecture. So yeah, I always advise to my students of, you know, whatever you do, publish, put your work out there, make sure that everyone's aware about what you're doing. And that's really how you gain context. That's how you advance this research, really.
Natalie, I had one question real briefly is, if everything aligned and you became like the dean of the GSD or MIT and you had your own vision, what would be a great way to drive the students in the community? Is it to challenge the National Science Foundation, the granting bodies that give you money, or is it about the people, the bottom up? Neil posted that in the comments.
I would say what would be encouraging for students within Biodesign is actually showcasing applications with this research within the architectural discipline. So I guess it goes back to that conversation of how to incorporate academic research within the industry. I think when students see, oh, I can actually apply this research and these tools to architectural companies, I think that is quite inspiring. So if I was in that position, I think that's something that I would definitely push for, creating collaborations with industries.
Yeah. Thank you. I wanted to address one of the questions from the chat. It's to Natalie before you have to leave us. So it's from Dilara Özlü. And she asked, first of all, I want to thank you all. All presentations were wonderful. My question is to Natalie. Did the fabrication happen in a sterile environment? If not, how did you control contamination? So it's really hands-on question, but I think it's bringing up an interesting topic about lab work and sterile environments. So maybe you can speak to that briefly.
Yep. So most of the prototypes weren't created within a sterile scientific environment. There were, but obviously I try to maintain as much cleanliness within the organism as possible, just to avoid contamination. And there are definitely DIY hacks out there that you can adopt in order to avoid that. So I think, again, the great thing about Biodesign is, architects are now adopting scientific techniques that would ordinarily occur within the lab, and we're creating this DIY hack style within architecture that I think is really quite interesting.
Thank you. And maybe that leads to another question that I wanted to ask you, all of you, for young people that are interested. I mean, all of you, which I really enjoyed, shared DIY hacks and like recipes, basically how to get started. But what would be your advice for someone that's young, starting off maybe in their like early bachelor, to get involved in that? What brought you into this subject, and how would you advise people if they're interested in it to get involved?
I can
Great
start
question.
as like the most the youngest probably here. My background is environmental science. The education that brought me into biodesign is the realization of the whole trajectory of my consumption. It's understanding how little behaviors in my daily life are having great influence in the environment. I think start really small, like observe how your daily consuming behavior have a long and giant connections back to the environment. And you don't really have to know a lot of biological or ecological knowledge to be able to start, just by start observing how your daily little behaviors are connected to the natural system.
Thank you. Anyone else want to share? Maybe Joanna, how did you get involved with biodesign, and what do you think, other people can do if they want to move into this field?
So I was just inspired by, I think IAC did a lot of research and even like the cookbook of the biopolymers. So I just had really fun experimenting with the materials and also adding my perspectives into it. Whatever I found interesting, And well, I just had a lot of fun doing the biopolymer on my own, basically, which is like from the raw resources. So it's very satisfying, I guess. That's the I think the most important issue I had at the beginning of the research. And then it just went very smoothly because I found a lot of research, like Mary Oxman, for example, which was developing the whole process of fabrication. So there's a lot of resources we could use, but we just need to search for it and research it. Yeah. Be curious.
So Joanna, you bring in a good point. It's like you have to look for it. And I remember at one point when Mel scripting and then Python scripts for Rhino started to come out, there were websites that just had every script to make anything, right? But it seems like we're post that now. We have to share knowledge. Is there like an open source? I guess my question is, what does each one of the panelists think about open source knowledge? Is it about believing in the building of knowledge? And then also, how is COVID-19 complicated this issue? Like, we can't even come together and work with robotics or materials together without being at risk of infection or harm.
So yeah, how has each of you kind of bridged that right now? I mean, most of you might not even be able to go to their labs or teach the way that you used to teach during COVID. So maybe you can share a little bit about how you work, but also how it has changed during the COVID-19 pandemic, how you bridge that.
I think I would like to mention something about the open source question Gustavo was mentioning. I think it's a really important aspect of our lives nowadays, because nothing can build out of nothing. I mean, it's really important to build the knowledge step by step. We wouldn't be able to do any of this without previous knowledge. So it's really a key factor nowadays, I think, to develop work farther, or even farther than you would be able to do doing it all by yourself from scratch, let's say.
Yes, thank you.
Benjamin, do you want to speak about, what your thoughts are? Do you work with people in the lab?
I've started during the pandemic, so I don't know how it is. And I was lucky this November. I showed you the pictures because in Dessau the numbers were so low we could go to the lab. So that changed before Christmas, but there was a really good moment also to work with the students and work on something, and not before that I was also allowed to go to the lab but not do anything, no courses, no workshops. So with the minds of many, you can create so much better things. So I think especially for all these projects we saw today, it's not really helpful not to work together in the lab. So I hope that changes soon.
Thank you. I mean, yeah, I always see it as a moment in time that kind of makes us all reconsider and rethink how we've been working. And I think relinquishing control is one of the biggest things that had to happen automatically during this pandemic, because you cannot control everything. And I think architects are perfectionists and want to oversee everything, but at the same time, it's very important. And I think all of you have shown that you kind of collaborate, and that you can't do this all by yourself. So I think as this moment that we all are in different places and are kind of lacking that social interaction, I think it's really great moment to reconsider what it actually means to collaborate and how important and how beautiful it is. So thank you all for sharing. And I mean, what we do right now is literally like sharing and collaborating in a way too, because you share your thoughts, and that's really important to us. So thank you.
Well, I just wanted to jump in quickly. Joanna, does anyone want to talk about maybe working in firms right now? Is everyone packed next to each other 2 feet away on a computer? Or, you know, how do you guys see working collaboratively? I think I'm, you know, I basically had to watch 6 hours of tutorials before I went into the lab because there are problems with just what we know in science. Joanna, do you want to say something? Or Jessica?
Sorry, was the question about the office, how it works, or?
Yeah, like, or just your collaboration, just working with others right now. How is it?
Yeah, it's the thing is, like, I'm in Japan right now, and in Japan there's not many like cases. So it's basically as usual. The only difference is that we need to wear the masks. But if of course, if you want to work remotely, you can do this. But the thing is, like, working requires out of interactions between each other, and it's like not so so good as it was before face to face, right? So we always prefer to meet each other face to face.
Yes, thank you. If there's no further questions, I don't want to keep you, Joanna, and Natalie too long, but thank you everyone for your contributions. Now is the time to ask each other last questions, questions from the audience. There's only one question. One question for the panel. In your practice, have you found a connection with LCA for real world development? I don't really know if anyone knows an answer to that. Did anyone want to respond to that? It's from Pablo Vaquero in the YouTube chat. Maybe someone can clarify what LCA is. I don't actually know exactly. Does anyone know?
Life cycle assessment.
Okay. Did anyone want to respond to that? Or Sina, did you want to respond to that? Maybe you can inform us what LCA is.
I have to also look into the question then.
I can repeat it. In your practice, have you found a connection with LCA for real world development? I think it's very technical, so I would not respond. But if not, we can leave it at that. I just tried to give a chance to address that question. But maybe, yeah, maybe.
Yunin just replied in the chat. It's life cycle assessment.
Yeah.
Yeah, sorry. I did a little bit of research around LCA when I was trying to do an information design around it to raise environmental awareness. Currently, there are some carbon footprint assessment that is being printed into the products, which is, I think, performed by the Carbon Trust in UK. And since the data is really hard to collect and a standard is very different from different places, so right now it's still quite hard to collect all the holistic database for reliable LCA, for different environmental polluting attributes to really implement it.
And maybe I can shortly also add, we had this reference, Soybean Car by Henry Ford. If you think of planting soy and how much water you may need for that. So maybe at the end, a car made of soybean won't be, let's say, more sustainable than a normal car that we use today. But I think those kind of, let's say, restrictions may not stop us from experimenting, because maybe in the long run we would also have a better, let's say, agricultural system to support planting bio-based materials. I think it depends what sort of hypothesis we set for our research, and how do we set long-term and short-term vision, and how we change the infrastructure, so to say.
Yes, thank you, Sina. So if there's no further question from anyone, I would like to thank our speakers. Thank Gustavo for co-hosting with me. It was a pleasure and a great way to start the new year. So thank you, everyone. And next Saturday, we have another session coming up. It's Local Voices. So we're gonna transport ourselves into the Amazon and talk about the rainforest. So it's going to be a really interesting discussion, and I think we'll touch on similar points in terms of, you know, how do we move forward into the future together. So thank you, everyone, and have a great rest of the day or a great good night.
Sorry, I just wanted to say one thing, that I wanted to thank all of our panelists. I wanted to thank the Digital Futures community and team, and I wanted to especially thank my co-moderator, Victoria. She is awesome, and happy 2021.
Thank you, everyone. Bye-bye.
Bye.
Thank you.
Thank you.